All right, so I'm going to be working through all the problems in this practice review, which was posted for Dr. McKeown's class. And I'm just going to dive right in. So looking at problem number 1. So we're given an ellipsoid S, and then we're given this vector field F, and then we're asked to compute this flux integral of our vector field over the surface S. Okay, so there are two ways that we can go about this problem, and I will go ahead and mention both of those methods. All right. So let me write down some of the information from this problem first. So S is an ellipsoid, and here was its equation. And then the vector field F that we are trying to integrate. Okay, so let's see here, x squared y minus 2xyz minus x y e to the y. The second component is y e to the y minus x y squared. And then the third component is y z squared minus z e to the y. Okay. All right, so in order to compute this flux integral of our vector field F along the surface of the ellipsoid. Okay. So again, there's two ways of going about this problem, and I'll kind of talk about both ways. So we'll call this one method 1 first. So method 1 is to just evaluate the flux integral directly. Okay. Method 2 is to use Stokes' theorem, or sorry, not Stokes' theorem, but so use the divergence theorem, which I guess is a special case of the general Stokes theorem. Okay. But I'll talk about that method later. Right now, let's talk about how we would try to evaluate this flux integral directly. Okay. So let me kind of explain the general procedure for evaluating a flux integral. Okay. So the first thing you want to do is you want to come up with a parameterization for your surface. Okay. All right, so S is your surface, and you want to parameterize it. So to parameterize it is to come up with a function, which I'm going to call sigma. Okay. Now, when you're parameterizing a surface, you're going to come up with a parameterization, which will be a function defined over some subset of R2, so the xy plane. And then it's supposed to map this region onto your surface S, which would generally be a subset of R3. Okay. And so I'll use U and V for the arguments of the parameterization, although in general, the arguments are just whatever you choose them to be, whatever letters you choose to use. Okay. So you come up with this parameterization. It maps into R3, so it's going to have 3 components to it: an X component, a Y component, and a Z component. Okay. All right, now after you get this parameterization, then what you'll need to do with it is you'll need to use your parameterization to compute the or to compute a normal vector to your surface. All right, so to do that, what you're going to do is you're going to compute the partial derivative of your parameterization with respect to u. So that would just be doing the partial derivative of each component with respect to u. All right, so you're going to do the partial with respect to u as well as the partial with respect to v. And after you compute these 2 partial derivative vectors, you're going to cross each of them to take their cross product. Okay. Okay, so then after you compute the cross product, then you can go ahead and evaluate the flux integral now. So the way you do that is so by definition, to evaluate this flux integral, you're going to set it up as a double integral. Okay, now, the integral is going to depend on your parameterization. So whatever the domain of your parameterization was, which I'm calling D right now, that's going to be the region of integration over here. And then what you do inside is you're going to have your vector field, F, but it's evaluated along your parameterization. So you're going to have that, and then you're going to do the dot product with the cross product vector that you computed over here. And dot product with sigma u cross sigma v. Okay. And then u and v would be your variables of integration. So here you could have a du dv, or possibly a dv du, depending on whichever order may have seemed more convenient for you. Okay. And then this part here, where you're plugging your parameterization into your vector field F. So that amounts to plugging in the X component of your parameterization, and for X, and then likewise plugging the Y component of your parameterization into Y, and so forth. Okay. So that's kind of the general outline of how to evaluate a flux integral. I guess this is the definition of how to evaluate a flux integral. And I'll set up the flux integral for this problem as well. So let's see how we will do that. So the first thing we need to do is parameterize our ellipsoid. Okay. So to parameterize an ellipsoid, we can use spherical coordinates to parameterize a sphere, and making a modification of spherical coordinates would give us a parameterization of an ellipsoid. So let's see how that works. Okay. So first, let's recall the equations for spherical coordinates. Okay, so the equations, x was, let's see here, rho sine phi cosine theta. Y is rho sine phi sine theta. And then z is rho cosine phi. Okay. And then I'll just draw a little picture of what everything represents. Okay. So rho represents distance from the origin. Theta is the usual polar coordinate angle. So if you project a vector or a point down into the xy plane, then the polar coordinate angle of its projection, that would be theta. And then phi represents the angle measured from the positive z-axis outwards. So then this angle would be phi. Okay. So from these equations for spherical coordinates, if you want to parameterize a unit sphere. Okay, so to parameterize a unit sphere, your rho, the distance from the origin of every point on the unit sphere, would be equal to 1. So if I simply plug in 1 for rho into these equations, so this would give you a parameterization of the unit sphere. If I wanted the entire sphere, I would need theta to range from 0 to 2 pi to go around full circle. And phi, we'd want phi to range from 0 to pi to get the entire sphere. So we'd get everything from up here all the way to the bottom. Okay? All right. Okay. And then these equations, they're going to satisfy the equation of a sphere, of a unit sphere, which is kind of how we can sort of verify that it is a parameterization of the unit sphere. Okay. Now, we have an ellipsoid. So what we have is the equation x squared plus 2y squared plus 7z squared equals 1. So to come up with a parameterization for this ellipsoid, I want to use the parameterization of the unit sphere that we have up here to help me to do that. So what I'm going to do right now with my ellipsoid equation is I'm going to rewrite it slightly. See, I think I'm going to write this as, let's see here, square root of 2y squared, and then I'll write this as square root of 7z squared. Okay. Okay, so then what I'm going to do is I'm going to sort of treat this as like a new y, at least for the moment, and I'll treat this as like a new z for the moment. And I'm going to, so then this would look like an equation of a unit sphere, like x squared plus new y squared plus new z squared equals 1. So then I could parameterize it by using my spherical coordinate equations up here. But what I would have is x would be, sine phi cosine theta. But then instead of y being equal to this, my y is at really square root of 2y. So I'm going to do that equals sine phi sine theta. And then my z is really square root of 7z in this equation. So then we'll have that equals cosine phi. And then what I can do is I can just divide the square root of 2 and the square root of 7 to the other side. So that way everything is in terms of the original x, y, and z. Okay. All right, so then this would give us a parameterization for our ellipsoid S. Okay. So specifically, I could use these three equations to define my parameterization sigma. So instead of using u and v, I'm using phi and theta for the variables. So then this would be the x component of my parameterization. Okay. And then I would use this for the y component of the parameterization. And then this would give me the z component of the parameterization. Okay. And then as noted earlier, I'd want theta to go from 0 to 2 pi, and I'd want phi to go from 0 to pi altogether if I want the entire ellipsoid. Okay. So now that we have this parameterization of the ellipsoid, all right, so the next step, if you will, in the process is to come up here real quickly. So now I need to compute these partial derivative vectors and take their cross product. So that's the next step. Here I'd be doing the partial derivative with respect to theta and phi. So let's start with the partial derivative with respect to phi, which I guess maybe, I don't know, maybe you guys would prefer to write it like this. So I'll write it like this. Okay. So doing the partial with respect to phi is going to be cosine theta, cosine phi, cosine theta. 1 over root 2 cosine phi sine theta. And then let's see here. Last one will be negative 1 over root 7 sine phi. Okay. Then we'll need the partial derivative with respect to theta. Oh, and again, I guess I'll write it like this perhaps, because you guys might prefer that. Okay. Let's see here. So with respect to theta, this would be negative sine phi sine theta. 1 over root 2 sine phi cosine theta. And then the last one with respect to theta is 0. And then what we need to do is compute the cross product of these two vectors. Okay, so here I'm just going to set up the 3 by 3 determinant for the cross product. All right. So let's go ahead and do this cross product. It's going to be, let's see here, 0 minus negative. So let's see, 1 over root 14 sine squared phi cosine theta. So next is going to be, let's see here, 0. It's ultimately going to be minus 1 over root 7 sine squared phi sine theta. And the last one is going to be okay, so 1 over root 2. So multiplying these together first, so it'll be cosine phi sine phi, and then also cosine squared theta. And then next you'd get minus a negative, so it'll be plus 1 over root 2. You get cosine phi sine phi. And then also sine squared. Okay. Now this last term, we can actually simplify it quite a bit. So notice that we can factor out the 1 over root 2 cosine phi sine phi from both terms. Doing so will leave you with cosine squared plus sine squared. And we know that that is all equal to 1. So ultimately, the last component would just be 1 over root 2 cosine phi sine phi. All right, great. So then now that we have the cross product there, we can go ahead and move on to the third step, is to evaluate the flux integral directly. Now let's see here. So I'll go ahead and set it up for everyone. So first we'll be doing a double integral, so let's see here. Okay, So we'll be integrating with respect to the variables phi and theta. And from our parameterization, we have these bounds on the variable. So those will be the bounds on the integral. Let's go ahead and do 0 to pi, 0 to 2 pi. We'll have d theta first and d phi last. Okay. Now on the inside, what we would be integrating. Okay. So here what we're supposed to be integrating is our vector field f evaluated along our parameterization. And then dot product with the normal vector that we obtained by doing this cross product here. No, I guess instead of u and v, I'm using phi and theta. Okay. Okay. All right, so let's see how that is going to work. So first, so this was the vector field originally. So I'm just going to write it down again. Okay. And then I guess let me go ahead and write down the parameterization sigma that we had earlier real quickly. Okay. So for this first part over here, plugging our parameterization into the vector field f, that amounts to plugging these three expressions in for x, y, and z. Okay. So let's see here. So that's going to be really messy, so I probably won't write it all out. But so we'd plug this in for x. So the first component would be x squared times y and then we'd have minus 2xyz, so minus 2. So then xyz is multiplying all three of these together. So multiplying them together gives us 1 over root 14. Sine squared phi cosine phi. Cosine theta sine theta. And then lastly, you also have this minus xy e to the y. Whoops. And again, you have to plug all this in for x and y. So it'll be x times y and then times e to the power of y All right, and then it's getting pretty big, so I think you guys probably don't want to see me write it all out, but you would continue plugging everything here in for x, y, and z to get the remaining two components of your vector field here. And then whatever resulting vector that you get from this, you're going to then need to do a dot product with the cross product vector that we computed up here. Let's see here, I wonder if I can copy paste. I'm not an expert at this stuff yet, so let's see. Oh, okay. I guess you guys get the idea. So you'll take this vector, and you'll need to do the dot product with the vector that you got over here. Ah, there you go. All right. Okay. And then, maybe lots of things cancel out and you get a really nice expression left over. But whatever you get from that dot product, that's what you're going to put inside the integral here. And then that's where you're going to end up evaluating, all right? So that's method one to this problem, which is evaluating the flux integral directly. Now, I'm hopeful that the second method, which is using the divergence theorem, which is also known as Gauss's theorem, and I guess also known as Stokes' theorem, I'm hoping that second method will be easier, or at least not as messy, but we'll see, okay? Just a quick recap though, here's the general three-step procedure for evaluating a flux integral directly. Okay. So again, just to recap this part. No, whoops. So whatever your surface is, you want to come up with a parameterization for it. For a sphere or an ellipsoid, a modification of your spherical coordinate equations can be used to get a parameterization for it. Once you get your parameterization, you're going to compute these partial derivative vectors and compute the cross product. Once you have that, then you're going to evaluate the flux integral by doing the double integral over this region D, which was the domain of your parameterization. And you're going to need to compute this dot product between your vector field evaluated along the parameterization, and then dot product with this normal vector that you get from the cross product. Okay. All right, but let's take a look and see if method two will be a little bit easier for this problem. I guess I'm just going to do it over here. So first, let's talk about what the divergence theorem says. Okay, so if we have a region in R3, so let's say it's some kind of closed region like this. I'll call this region including, so it's the entire volume, if you will, including the inside. So I'm going to call all of that, I'll call it R, okay? Okay, so this region should have some volume to it. So it shouldn't be like a flat area, if you will. And the boundary of this region, people often use this like kind of partial derivative notation for the boundary. So it's like partial r, but it's not representing an actual partial derivative, but it's just representing the boundary. So the boundary of the region R would be just this like exterior layer. So it's just a surface that has like a surface area to it, and it's not including the region on the inside, okay? All right. So if you have a flux integral that you're trying to compute over this closed surface, by closed surface, we mean a surface which encloses some volume. So that's the boundary of region R. Okay, so the flux integral of a vector field over the surface, so it's equal to the triple integral over the entire region R, so over everything inside as well, of the divergence of F. And then maybe I'll write dB. Okay. All right, so a couple of things about the divergence theorem. So first is something that I didn't talk about before when I was talking about flux integrals. So when you do the cross product of these two partial derivative vectors that you get from your parameterization, so this cross product represents like a normal vector to your surface. And in general, when you have a surface like this, which encloses some volume, there will be like, well, in general, there's always two choices of a normal vector. And for a surface which encloses some volume like this, you'll have one normal vector which will be pointing like outwards. And then you'll also have a normal vector which is pointing inwards. And so depending on the parameterization that you choose, you may end up getting one that gives you the outward pointing normal or one that gives you the inward pointing normal. And the only difference that's going to make in your flux integral is it's going to affect the sign of the result. So parameterizations that give you a normal vector pointing in one direction will give you one result for the flux integral, and parameterizations giving you the normal vector in the opposite direction will give you the same results, but just opposite sign. Okay. Now, for the divergence theorem, though, specifically, this guy has to be oriented using the outward pointing normal vector in order for the divergence theorem to work. Okay. So if you use the outward pointing normal vector, then this flux integral will equal this triple integral. If you use the inward pointing normal vector, this would be equal to the negative of this triple integral instead, is what would happen. Okay. But as to how we can apply this in our problem, so remember that for us, we had the surface at, whoa, okay. Okay. All right, so for this problem, we had the ellipsoid S. And here I'm just going to draw a generic picture of an ellipsoid. Okay. So the ellipsoid S does happen to enclose some volume. So I'll refer to the entire volume as E, I guess, for ellipsoid. So E is like the ellipsoid S plus the region that's enclosed in it as well. So it's a region with some volume to it. It's three-dimensional. Let me see here. Okay. So because we have a surface enclosing some volume, we could try to apply the divergence theorem. And so the divergence theorem would allow us to evaluate this integral, this flux integral here by instead doing the triple integral of the divergence of f over the entire region that was enclosed by our surface. So let's take a look at what the divergence of f would look like. Maybe that turns out to be something relatively simple, and then maybe evaluating this triple integral would be easier than evaluating this flux integral. Okay. Okay. So first, let's try to compute the divergence of our vector field. So let me see here. So here's the vector field F that we had earlier. Okay. So to get the divergence, so remember, to get the divergence, you do the partial derivative with respect to x of the first component of f. And then plus the partial with respect to y of the second component of f. And then plus the partial with respect to z of the third component of f. All right, and so doing the partial derivative, it's going to be 2xy minus 2yz minus y e to the y. So looking at this one here, doing the partial with respect to y, so there's a product rule that we'll need to use for this first part. So it'll be derivative of the first times the second plus the first times the derivative of the second. And then this one with respect to y will be minus 2xy. And then here, partial with respect to z will be plus 2yz. And then minus e to the y. Okay. So here, looking at the divergence, it seems to simplify quite nicely. Oh, that's rather amazing. Okay. So in fact, the divergence of f looks like everything cancels, so it is actually equal to 0. Cool. So then in that case, we know since the divergence of f is 0, this triple integral will be equal to 0 as well. So then incidentally, that would have been the answer to the first problem. The flux integral should have been equal to 0. Okay? All right. So just to sort of recap I think the important part though, which is the divergence theorem. So if you have a surface which encloses some volume, then to evaluate the flux integral of a vector field over that surface, if you orient it with the outward pointing normal vector, you can evaluate that integral as a triple integral over the region enclosed by the surface of the divergence of your vector field, okay? So if you see a problem like this, which is asking you to evaluate a flux integral over a surface which encloses some volume, like an ellipsoid, and if your vector field looks, incredibly complicated as it was in this first problem, then it could be set up so that the divergence of that vector field would be really simple. And thus it would simplify things if you use the divergence theorem to evaluate it, okay? All right. Now that being said, I think you might have to perhaps evaluate a flux integral directly on your exam. So that is why I did want to kind of go over how you would do method 1 still, okay? All right. Okay, but that was a lot. So let's go on to the next problem. Okay, so you have the function f, and you're finding the extrema on the ellipsoid. Okay. Okay, so this is a Lagrange multiplier problem. So we are trying to find the extrema of a function, but we're being constrained by some equation, okay? Okay, so then this function that we have in the constraint equation, so I'm going to call that function g, and then f is the function that we were trying to find the extrema of. So a quick reminder of how Lagrange multipliers works. So basically, you take the gradient of f, you take the gradient of g, and you set the gradient of f equal to lambda times the gradient of g. This will give you a system of equations. And together with the system of equations, and then also with your constraint equation, your constraint equation will be of the form g of x, y, z equal to some constant. You use the system of equations. To find x, y, z, where your function might have extrema. Okay. All right, now, you might find multiple points when you're solving this system of equations. So if you do find multiple points, you can plug them into your function to see which one gives you the largest value, and then that would have been like your maximum. You can plug in, and like whichever one gave you the smallest value would have been your minimum, okay, for this type of question here. Okay. Now, I guess for this problem, there is a nice simplification that we can make. So our function f, notice that is defined as an exponential function, right? E to some power. Now, the exponential function is naturally an increasing function. So the larger the exponent is, the larger the exponential, and the smaller the exponent, the smaller the exponential. So because of this property, that means that, when is our function here going to be maximal on this ellipsoid? Well, it should be maximal wherever its exponent is maximal on the ellipsoid, and likewise, f will achieve its minimum on the ellipsoid wherever its exponent achieves its minimum. So in other words, rather than optimizing the exponential, we can optimize its exponent instead. Okay, and that would probably be a little bit easier to do just working with the exponent rather than working with the entire exponential. Okay. You can do this for any increasing function. So, for instance, natural log is also an increasing function. So if you had natural log of something, you could just optimize what was inside the natural log. And you can incorporate the exponential and the natural log at the end if you need to. But So let's illustrate that with this problem. So what I'm going to do is I'm going to ignore the e right now and just focus on the exponent of f. So I guess what I will do is I will call this, I'll call it h, since it's not the same as f. So I'm going to optimize h subject to the constraint of being on the ellipsoid. So I'll do Lagrange multiplier on these two functions. So let's do gradient of h. So partial with respect to x, with respect to y, with respect to z. Partial of g, which was our constraint function. So partial with respect to x, with respect to y and z. And then we're going to set the gradient of h equal to lambda times the gradient of g. So that's going to give us 2x equals lambda 2x. Uh, 4y equals lambda 8y, and 6z is lambda times 18z. Okay, so then let's see what we can do with this. Okay, so it looks like I'm gonna consider a couple of different cases here. So let's start with the first equation, 2x equals lambda 2x. Okay. So from this equation, so there's two possibilities. Either lambda is equal to 1. But wait, I guess let's see here. So it looks like lambda might be equal to 1, but if lambda were equal to 1, see, that will give me 4y equals 8y, and 6z equals 18z. But then the only way for these to be possible is if y and z were both equal to 0. Okay, so if y and z were equal to 0, then going back to the equation of the ellipsoid, so our constraint equation, so x squared plus 4y squared plus 9z squared, but y and z are both 0. So therefore you get x could be plus or minus 1. So right now that gives us two potential points where we might have a max or a min. Okay. Now if lambda is not equal to 1, then here the other possibility would be that x would have been equal to 0 perhaps. Okay. So if x is equal to 0, then plugging that into our constraint equation will leave us with this. And then we're still left with our two equations over here as well that we haven't done anything with yet. Okay, and then I guess I'll just kind of try to continue this logic. So let's look at this next equation here. So in order for 4y to equal lambda times 8y, so one possibility is that lambda would be equal to 1/2, so that you get 4y equal to 4y. But if lambda were equal to 1/2, then down here you would get 6z equals 9z. And then the only way for that to be possible would be for z to be equal to 0. Okay. So then if x is 0 and z is 0, then coming back to our constraint equation, you would just have 4y squared equals 1 remaining. So y squared would be 1/4. So y would be plus or minus 1/2. And that gives us another two possible points where we might have a max or a min on the ellipsoid. Okay. And then if lambda is not equal to 1/2, then this would still be equal if y were equal to 0. And then if y is 0, then we would just have in the constraint 9z squared equals 1 remaining. So z squared is 1/9, and z would be plus or minus 1/3. Combined with y is 0 and x is 0, give us two more possible critical points, if you will. Okay. So we had these 6 points in all. So I'm going to plug them all into H to see which one gives me the largest value and which one gives me the smallest value. I'll just do it over here. Okay. So when I plug in the first, so you would plug in 1, 0, 0, and then plug in negative 1, 0, 0. Now in this case, because the x is getting squared, then they'll both give me the same value, so I can kind of just do them both at once. So it'll just be 1 plus 0 plus 0. Let's see, if I plug these points in next. So again, I guess in general, you plug them in one at a time, but since we have y squared here, they'll both get the same value, so I can kind of do both of them at once. So that's going to be 2 times y squared would be 1/4. Excuse me. And then finally, plugging in the last pair of critical points. Again, you would, in general, plug them in one at a time, but they'll both get the same value because the z is getting squared in our function h up here. So it'll be 3 over 1/9, so it'll be 1/3. Okay. All right, so then between the values of 1, 1/2, and 1/3, 1/3 gives us the smallest values, so that would be where the minimum is occurring. And then 1 is the largest of the 3 values, so that's where the max would be occurring. Now, so then going back to the original function f, so remember that f was e to the h, if you will. So you can say that function f will have a max. Well, first its max value would be not 1, but f is e to the h, so its maximum value would be e to the 1. And that maximum occurs at these 2 points on the ellipsoid. And then likewise, f will have a minimum value of not 1/3, but e to a power of 1/3, because remember h was just the exponent. And then that minimum occurs at these 2 points of the ellipsoid, okay? Whew, all right, so that is the second problem. Let's move on to the third problem on this review. So here we're given this vector field f, and we're trying to evaluate the line integral over this unit circle. Okay. So I'll write down some of that information. Here is the vector field. Looks pretty messy, so okay, so that's f. So C is so C is the unit circle in the plane z equals 0, so that would be in the xy plane. Okay, and it's positively oriented, so positive would be like a counterclockwise orientation in the xy plane, so it'd be like that. And then we want to evaluate the line integral of f over this circle. So just like in problem 1, there are 2 ways that we can approach this problem. And again, probably one way is really messy and one way is going to be much nicer. But nevertheless, I'm going to go over both methods, all right? All right, so method 1 would be to just evaluate this line integral directly. Method 2 would be to use Stokes' theorem, but just because I think it's important to yeah, sure. So just because I think it's important to talk about how to evaluate line integrals directly, so again, I'll at least kind of walk you through the procedure and set it up. But I suspect, again, just like how we saw in problem 1, probably the integral will be really nasty, and so probably I'm not going to actually work it out completely, okay? So the procedure for evaluating a line integral is very similar for the procedure of evaluating a flux integral. So first thing you need to do is parameterize your curve. So just like how we had to parameterize the surface for a flux integral. All right, so I don't know what notation you guys usually use. I'm going to use notation S of t. Okay. So you'll parameterize your curve by, so that means to come up with a parameterization for it. So the parameterization will be some function of, this time a single variable. Okay. And so, let's see here, your parameter t will be, restricted to some interval for your curve. So it'll depend on your curve and your parameterization that you chose for it. And then let's see here. I guess for the flux integral, you have to compute the two partial derivative vectors and take the cross product to get a normal vector. Here, fortunately, you just need to compute the derivative of your parameterization to get a tangent vector to your curve. And then to actually evaluate the flux integral. So it'll be set up as an integral from a to b dependent on your parameterization. And then it would be your vector field f evaluated along your parameterization. And then dot product with the, derivative of your parameterization, so the tangent vector that you computed earlier. Okay. Okay, so in order to parameterize a circle, you can use polar coordinates for that. So we have like x is r cosine theta, y is r sine theta, and since I'm parameterizing a unit circle, I'm going to have r equal to 1. Okay. Now technically, since our vector field has 3 components to it, so technically, I'd want something for z as well. Since we're in the plane z equals 0, we would actually just have z as constant equal to 0 then, okay? So this is giving us a parameterization s of, and then I'm using theta instead of t for the parameter. Okay, but we have s of theta, the x component is cosine, y component is sine, z component is 0, okay? And to get the entire circle, we could have theta ranging from 0 to 2 pi. Okay. So let's compute the derivative of this guy real quickly. So derivative would be negative sine, cosine, and 0. And then finally, to evaluate this integral now, so we'd be setting it up as an integral from 0 to 2 pi, an integral with respect to theta. And let's see here. So what we're going to do is we're going to take our vector field f from the problem. So what we need to do is evaluate our vector field along the parameterization. So similar to what we did with the flux integral earlier, that just amounts to plugging these in to the vector field for x, y, and z. So like for x will be replaced with cosine, y will be replaced with sine, so it's cosine squared theta times sine theta plus e to the 0. Next will be z is 0, cosine is 0 is 1. Here x is cosine squared, so x squared is cosine squared, and then z is 0, so e to the 0 is 1. Okay. So then this would be the vector field f, but evaluated along the parameterization that we chose. And then we're doing the dot product with, whoops, I keep using R, but I want to use S. Okay. And then we need the dot product with the derivative of our parameterization. So dot with negative sine theta, cosine theta, and 0, and then d theta. Okay. Now in this case, I suppose it's maybe not that bad. So we have the integral from 0 to 2 pi. Doing the dot product will give us negative cosine squared, sine squared. And then also minus sine distributes to plus 1, so we'll get minus sine theta. Then we'll have cosine times 1. And then we'll have 0 times that. So then it'll be integrating all of this with respect to theta. That's not too bad, so you can actually work out the rest of the integral from this, okay? Let's see here. Yeah, okay. I'll leave the integration work to you guys, all right? Okay, so this is one way of going about this problem, just evaluating the line integral directly. The other method that you could apply for this problem is using Stokes' theorem. So let's talk about how Stokes' theorem would work. So first, let's talk about Stokes' theorem. So it's similar to the divergence theorem that we talked about in problem 1, although it is a little bit different though. So for Stokes' theorem, let's imagine that we have some kind of a surface in R3. I'm just going to draw a sort of generic kind of a wavy sheet. Okay. Okay. So whereas for the divergence theorem, you needed a surface that enclosed some volume. Here for Stokes' theorem, you want a surface in R3 that does not enclose any volume. Okay. So something like a sheet, or you could also have something that's kind of like a bowl shape. Something like that. But it would be without the, so like not including this lid on the bowl, if you will. It's like just like an open bowl, okay? So for surfaces like these which do not enclose any volume, you can try to apply Stokes' theorem to them. So here's what Stokes' theorem says in this context. So whatever your surface is, I'll call it, I guess I'll call it, yeah, sure, I'll call it S. Okay. Now your surface is going to have a boundary to it. The boundary is going to be some sort of a curve. So again, I'll follow a sort of the customary convention to denote the boundary using this partial notation. So sort of like, so we're not actually doing any sort of partial derivative here, but just writing it as like partial s to represent the boundary. So in each case, the boundary is going to be some kind of a closed curve, which can give some kind of orientation to. And so Stokes' theorem says that the line integral of a vector field along the boundary curve is equal to the flux integral over the entire surface S of the curl of F, and then I guess dot d sigma was the notation that you guys use for a flux integral. Okay. Now, let me make a couple of comments about Stokes' theorem. So again, there's this subtlety regarding the orientation of things. So in particular, remember how I talked about for a flux integral? When you're doing a flux integral over some surface, there's always two possible choices of normal vector that you could use. For any given surface, one pointing in one direction, another pointing in the opposite direction. And depending on the orientation, which normal vector you end up using, that will affect the sign of the result of the integral here. And then likewise, when you're doing a line integral, the orientation of the curve also matters. So one orientation will give you one answer. Opposite orientation will give you the same thing but negative, or same thing but with opposite sign, rather. Okay, so for Stokes' theorem, you have to make sure that you choose the orientation of your boundary curve and your surface in such a way that they sort of are compatible, okay? And I'm just going to use the word compatible very loosely here. Okay. All right, now, to figure out if the orientation of your boundary curve and your surface, if they are compatible, I guess. So there's a sort of right-hand rule that you can follow to figure this out. So what you can do is choose an orientation for your boundary curve. So in each picture I have, whoops, I guess I don't need that. So in each picture I've already drawn the boundary curve to each of these surfaces, and I've already labeled some orientation on it. So now what I'm going to do is, so let's imagine drawing like a little square, like a little patch along a portion of the boundary. So since I've given my boundary curve orientation going this way, I'd give this patch an orientation like this then to match the orientation of the boundary. So then what I want to do is use the right-hand rule, and I want to take my right hand and curl my fingers in the direction of the orientation of this patch. So if I kind of curl the fingers of my right hand in that sort of orientation, that sort of direction, my thumb ends up pointing kind of upwards. Okay? So this tells me that for this orientation of the boundary curve, I would need to use a normal vector pointing more like upwards rather than downwards for the surface in order to get matching results on both sides of the equation. And then similar for like this kind of bowl-shaped surface. So imagine like drawing a sort of like rectangular patch, if you will, with part of it along the boundary. And then whatever like orientation your boundary has, that determines like an orientation on this patch. Then you take your right hand and curl your fingers in the direction of those arrows on that little like rectangle. And your thumb points in the direction of like the normal vector that you want to be using. So for this kind of bowl shape, my thumb is going to be pointing like kind of like more outside of the bowl rather than inwards. Like for me, my thumb kind of points towards me. So that means that you want a normal vector that's kind of pointing like outside of the bowl rather than one that's pointing more like inwards, okay? All right. So then when you're choosing a parameterization for your surface, you'd want to double check whether your parameterization gave you the normal vector that you wanted, whether it was pointing in the direction that it needed to or if it was pointing in the opposite direction. If it's pointing in the opposite direction, you can still use your parameterization, but when you evaluate the flux integral, it'll be the negative of the line integral that you were computing, though. With the like, if you chose an orientation for it like that. Okay, so that's a little bit of subtlety about the orientations on Stokes' theorem. Now that being said, it's not clear to me how much you guys really care about orientation. So I don't know, but let's see. Okay. Oh, let me plug in my laptop first. It's about to die. Okay, so let's let's see how we can apply Stokes' theorem to the problem that we have. So we have the unit circle in the xy plane as our curve. And we're doing the line integral of some vector field f along this curve. Okay. So this unit circle, we can view it as being the boundary of this unit disk in the xy plane. Let's call that D, that area, that disk. So then we could say that this line integral should be equal to the flux integral over that disk in the xy plane of the curl of vector field f. Okay. So let's go ahead and let's just compute what the curl of f was first. And then we'll take a look at how to set up the flux integral after that. I think it's still copied. Perfect. All right, so to compute the curl of f, remember that was a sort of cross product thing. So we do ijk, and then we write down the partial derivative operators for the second row. And here I will write down the components of f for the final row. And then we've got some, we'll evaluate this determinant to get the curl. So the first component is going to be 0. So that's going to be minus, so I'm doing the partial with respect to z here, so it'll be minus y. And then minus, and then cosine becomes negative sign, so double minus, so it's plus sign. Z cubed, and then there's a chain rule, so we'll get 3z squared on the outside. So next, we're going to get, I guess that would be negative 2x. Minus, but then another minus, so plus, and then partial with respect to z here would be 2z e to the z squared. And then the last one is 0 minus partial with respect to y, so the minus x squared. Okay, so that would be the curl. Okay. All right, so then we need to evaluate the flux integral of the curl of f, which we computed over here, over the unit disk, okay? So this one might actually be messier than evaluating the line integral directly. Because here we already set up the line integral directly, and it wasn't that bad. But nevertheless, let's at least set this one up. If it's regardless of if it's messy or not, it'll be good to see how to do it. So to evaluate this flux integral here, so first we have to parameterize the surface that we are working with. In this case, the surface we are working with was the unit disk D. And for a disk, we can parameterize it using, since it's in the xy plane, we can just use ordinary polar coordinates. So we'll do like x is r cosine theta, y is r sine theta, and since we're in the xy plane, z would be equal to 0. Okay. So I guess if you wanted to write it out, the parameterization would be r cosine theta for the x component, r sine theta for the y component, and 0 for the z component. To get the unit disk, we'd want r ranging from 0 to 1, and we'd want theta ranging from 0 to 2 pi. Okay. So then we need to compute these partial derivative vectors with respect to the two variables r and theta. So partial with respect to r will give us this. And then partials with respect to theta will give us this. And then we'll do the cross product of the two of these. All right, so if we do the cross product, it's going to be 0, 0, r cosine squared plus r sine squared, so just r. Okay. Now I'm going to pause for a moment. So here, this gives us our normal vector that we're using for at least this parameterization gives us this particular normal vector for our unit disk. Okay, now, I guess I want to make sure that the orientation matches with the orientation of the boundary curve, because we were actually specified a positive, so counterclockwise orientation on C. Okay, so let me draw, a picture here again. So here's the unit circle C in the xy plane. The positive orientation looks like this. Okay, so for this disk in the xy plane, so there are two possible normal vectors that we could use for the disk, one pointing upwards, one pointing downwards. Okay, so the parameterization that we came up with over here gave us an upward pointing normal vector. Upward because r is going to be non-negative, so upwards. And I just want to double check that this is the correct orientation for the normal vector that I'd want to use. So I want to make sure that's compatible with the counterclockwise orientation of the unit circle. So I'm going to do it the way that I described earlier. So I'm going to draw like a little square or rectangle, if you will, inside the disk with one edge along the boundary. That gives this orientation on that little rectangle. Now I imagine taking my right hand and kind of curling my fingers in that direction for that rectangle. When I do that, my thumb points upwards. So that tells me that the upward pointing normal vector is the one that is compatible with the counterclockwise orientation of the boundary. Okay. So in other words, I would be able to now evaluate the line integral of f as being equal to the flux integral of the curl of f. And specifically, I can evaluate this flux integral by using the orientation that we chose for it, for the disk, because this parameterization yielded the normal vector pointing in the appropriate direction. Okay, so let's remember how this works. So first, the bounds on the integral are determined by your parameterization. So we'll be integrating with respect to r and theta. The bounds on r are 0 to 1, and the bounds on theta are 0 to 2 pi. And then let's remember that we take our vector field, the vector field, which is the curl of f. It needs to be evaluated along our parameterization. And then we do the dot product with the upward, or the normal vector that we found with our parameterization. Okay. Now, in the event that your parameterization gave you a normal vector that was pointing in the opposite direction, so if it were opposite of the direction that you needed, you could just put a negative sign in front so that you get the correct result in the end. Okay. But since we have a parameterization that gives us the correct orientation, the correct direction for the normal vector, we would not need to put a negative sign in front. Okay. And then let's just see here. So this vector was 0, 0, r. I'm doing a dot product with the curl vector. So we computed the curl earlier. Let's take that result and copy it down. So that was the curl of f. Now, fortunately, so the x and y components were really nasty, but when we do the dot product, we'll multiply them with 0, so they actually don't matter. But the z component was minus x squared. Okay. And so what we need to do with that is, since we're evaluating the curl along our parameterization, then instead of minus x squared, we need to plug in for x from our parameterization. X is r cosine theta. Like that. So this would leave us with the double integral 0 to 2 pi, 0 to 1. Dot product would be, ultimately you'll have negative r cubed cosine squared theta dr d theta. Okay. All right. So either evaluating this double integral or evaluating this integral here, so evaluating the line integral directly, either of those two should give you the right answer for this problem, okay? Okay, so that was number 3. Let's look at number 4. I'll just move down. Okay. So we're given these two functions f and g, and we're just going to calculate the derivative using the chain rule. So that's actually pretty easy. So let's just remind everyone how that works. So this was f. This was g. And we want the derivative of g composed with f. All right, so remember that g composed with f. Let's see here. F is a function of x and y. Okay. So remember, this is what g composed with f is. So let's see here. In order to get the derivative using the chain rule, okay, so it's going to be the derivative of g evaluated at f of xy times the derivative of f evaluated at x and y. So it's like the derivative of the outside, but evaluated at the inside, and then times the derivative of the inside. Okay. Okay, so first let's compute the derivative of g and the derivative of f, okay? So the derivatives are represented as matrices. So derivative of f here, we would represent it as a matrix where the way I remember it is for the first column, I'll do the derivatives with respect to the first variable, so with respect to x. So partials with respect to x will be 2x, 2y, and 3x squared. Then partial with respect to the second variable, in this case y, will give me the second column. So partials of f with respect to y are 2y, 2x, and 0. Okay. I'll also need the partial derivative of g, which is a function of u, v, w. All right, so first partials with respect to u, vw and v minus w. So that's the first column. Partials with respect to v, it's the second column, and then partials with respect to w, give me the third column, okay? Now, here we have dg, but evaluated at f of xy. So that amounts to plugging in for u, v, and w, these three components of f. So we'll plug in x squared plus y squared for u. It was 2xy next, so that would be what you plug in for v. And the last one was x cubed, so that's what you'll plug in for w. Okay, so then here's dg, and I'm plugging these in for u, v, and w. So v times w, 2x to the fourth times y, u times w, u times v, v minus w, u, and then negative u, so negative x squared, negative y squared. All right, so that's dg evaluated at f of xy, and then we need to times df of xy, which was this over here. Okay, so you'll do the matrix multiplication, and then whatever you get as your result, that would have been at least the matrix representation for the derivative of g composed with f. Okay. So maybe I'll just do the first entry. So just remember for matrix multiplication, it's row dot product with column. So like for this first entry, it's the first row dot product with this first column. So we'd get 2x to the fourth y times 2x. Then we'll have this plus 2y. I'll just write it as it is. And then lastly, we'll have this times 3x squared. And so that would have been the first entry of this matrix. Okay. So then first row dot product with the second column gets you the second entry here. And then second row dot product with each column would fill out the second row here. Okay. But I trust you guys can do the matrix multiplication, so I'm going to stop at that point. So that was number 4. Let's look at number 5 next. Okay, so find and classify the critical points. Okay. So let's recall how this works. So first, what you want to do is compute all the partial derivatives of f, or if you will, you can think of it as computing the gradient vector. And then you want to find the critical point, so you want to take the partial derivatives and set all of them equal to 0. And then you'll solve this system of equations to find the critical points. Then we had the second derivative test to check if they yield a max or a min. Now here it's a function of 2 variables, but so that's a little bit easier to remember. But just in case you might see a function of 3 variables, I guess I'll cover the general second derivative test first. So what you do is you need to look at the Hessian matrix. So the Hessian, and I don't quite know what notation you guys use for it. I'll just use H for Hessian. Okay. So the Hessian matrix was the matrix of all the second order partial derivatives. So what you do is you take, so I guess I'll write it for a 3 by 3. I assume you won't see much larger than 3 by 3. In this case, it would only be 2 by 2 because it's 2 variables, but in case you see a function of 3 variables, I'll write it out for the 3-dimensional case. So you would take the partial of f with respect to x. So whatever the partial f with respect to x is, you'll do the partial with respect to x again. Then take the partial with respect to x, and then take its derivative with respect to y. Or actually, no. I mean, it doesn't matter, but I guess you do each of them with respect to x. Then next I would do partial of f with respect to y. But then partial of this with respect to x. And then I'd do partial of f with respect to z. So take this guy and then take its partial derivative with respect to x, and that will give you the first column. And then same thing, take the partials of f with respect to x, y, and z. And then take all their partial derivatives with respect to y. And then finally, take all the first order partial derivatives one more time. And now take all of their derivatives with respect to z. Okay. So that's the Hessian matrix for a function of 3 variables. So it should be a symmetric matrix. Because remember how mixed partial derivatives are supposed to coincide for a typical function. Okay, so yeah, you compute your Hessian matrix, and then the second derivative test says, let's say if C is a critical point of F, you compute your Hessian, and then you'll evaluate the Hessian at this critical point. And then if the Hessian evaluated at this critical point, if it is positive definite, then your function will have a local minimum at this critical point. And instead, if the Hessian evaluated at the critical point was negative definite, then F would have a local maximum instead. And then I guess otherwise it would have a, let's see here. I guess I would characterize it like this. So the other possibility is to have a saddle point. And so let's see here. I guess I don't think I've ever seen what the condition is for something higher than 2 dimensions, but if I had to take a guess as to what the condition for a saddle point is, so maybe I'll put a question mark because I actually don't think I've ever seen it before. But I guess it's just if the Hessian is neither positive definite nor negative definite. Well, I guess I want to say that it should have a positive and a negative eigenvalue. Well, okay, so I guess that's what I'll write down. So that should be correct, but I don't know if there's a better condition to check. Well, I guess you could say if it's neither But then you can't check that as well. Okay, well, I guess it doesn't matter. We'll see. Yeah, I don't quite remember. I guess I'd have to look that up. But for the two-dimensional case, I do remember what that was, though. Well, I guess no, that's just it was non-degenerate. Yeah. Well, okay. Well, all right. So that's the second derivative test. Now, okay, so then how do you check if the Hessian is positive definite or negative definite? So I guess we should go over that first. So to determine whether it's positive definite or negative definite, there is this theorem that says you can determine whether it's positive definite or negative definite or neither by looking at the determinants of each of these like upper left submatrices, upper left corner submatrices. Okay. So to be positive definite, you need the determinants of all of the upper left corner submatrices to be positive. Okay. So that means you would need this determinant of this 1 by 1 upper left submatrix. And the determinant of a scalar is just itself. So you would need this to be positive, the partial of f, or the second order partial of f with respect to x. But then you also need this 2 by 2 determinant to be positive. So take the determinant of this 2 by 2 matrix. And the determinant of this has to be positive. And then finally, you would need the determinant of the entire 3 by 3, so the determinant of the Hessian itself has to be positive, okay? So if all of those are positive, then it's positive, the Hessian is positive definite. Otherwise, it is not positive definite. Now, to check if it's negative definite, so you'll check the same three determinants, but this time to be negative definite, the first one has to be negative, and then it has to alternate in sign from there. Okay? All right. So then if you get anything other than all positive or alternating starting with less than 0, then you could not conclude that it was a local min or a local max. And then let me see here. Now, for the special case where your function is a function of two variables, I guess I'll just write it down here. Okay. So I know that for a function of two variables, So for your Hessian to be positive definite or negative definite, its determinant has to be, since you have two variables, you wouldn't have this third case. So the determinants have to both be positive. So the determinant of the Hessian would equal so you'd have the partial second order partial of f with respect to x times the second order partial of f with respect to y minus fxy squared. So if this is positive, okay, so then you'd have the second determinant already positive. So then you would need to look at the second order partial of f with respect to x. And if that's positive, your function or your Hessian matrix would have been positive definite. And then that means that you have a local min at this critical point. Whereas if it were negative to begin with, then it would have been negative definite. So that means that you would have had a local max. And then I do remember specifically if the determinant is of the Hessian at the critical point, if it's just negative, then I remember that would give you a saddle point because you'd have a positive and a negative eigenvalue if that were the case. I guess I could phrase it like this for this condition up here. So if the Hessian is not positive or negative definite, and if the determinant of the Hessian itself is non-zero, then you could say it has a saddle point for sure. Okay. Okay, so let's go ahead and work through this problem. All right, so the first thing you need is the critical points. So we'll take the partials of f with respect to x and y. And we'll set those equal to 0. Let's see here. So let me take the first equation and I'm going to factor out the x from it. So then that gives me two possibilities, either x is 0 or 3x equals 2y squared. Now if x is 0, then looking at my second equation, the fy equals 0 equation, and I plug in 0 for x, it will give me 3y squared equals 0. So therefore y must be 0, and that gives me one critical point. Now let's see, otherwise 3x is equal to 2y squared. Let's replace x with 2/3 y squared. So I'll plug that into this equation. Okay. So I'm going to replace x with 2/3 y squared. Okay. So let me see what that will give me. That will be 4/9. So -8/9 y to the 5th plus 3y squared is 0. So factor out a y squared, and we're going to get -8/9 y cubed plus 3 is 0. Now, one possibility is that y is equal to 0. But if y is 0, then we would get x is 0. But then we already had that critical point. So therefore, I just need to consider the other possibility that 3 is equal to 8/9 y cubed. So 27/8 is equal to y cubed. So cube rooting that, we'd get y is 3/2. And then we could plug that into here to get x. And I think you'd get x is 3/2 as well if you did that, okay? So it looks like we have two critical points, 0, 0, and then 3/2, 3/2. Okay. Now let me see here. So next, I need all the second order partial derivatives to get the Hessian. Okay, so doing the partials with respect to x will give me 6x minus 2y squared minus 4xy. That's also minus 4xy. And then partial of this one with respect to y is minus 2x squared plus 6y. Okay, so we plug in the first critical point that we found, 0, 0. So I guess incidentally, that's all going to be 0. So the second derivative test doesn't give us any information about it, so we might need to analyze it more closely. Let's try plugging in our other critical point. So if I plug in 3/2 for x, it's going to be 9 minus, and then see, we plug in 3/2 for y, that'll be 9/4 times 2, so minus 9/2. 9/4 times 4, so -9 for each of these. And then x squared is 9/4. It's -9/2 plus 6y, so plus 9. So let's see here. That's going to be 9/2 minus 9 minus 9 and 9/2. So first, let's check the determinant of the Hessian. So that's going to be, well, 9/2 squared minus 9 squared. and that's definitely going to be negative. So because it's Hessian is negative, it's neither positive definite nor negative definite, and we can also conclude that you'd have a saddle point. Okay, but let's go back to the original function. Let's try to determine if the origin was a max or a min or neither. Okay, so this was our function f. Yeah, so looking at this function here, I think the origin is neither a max nor a min. I'm pretty sure we could classify it as a saddle. And so the reason why I think that is because, so I imagine if I plug in just 0 for y, so we'd have f of x 0 would just be x cubed. And so I know that x cubed function, so when x is positive, it'll be positive. When x is negative, it'll be negative. So there are points that are close to the origin where your function will be positive and also where it'll be negative. So therefore, neither a local max nor a local min. Oh, and then I'm comparing to f of 0, 0 to 0, of course. And then because I kind of see this feature of how it kind of looks like a cubic, and that's kind of the shape of a saddle. So to me, it looks like it would be a saddle point, is what I would say. Okay, so I think I'll probably just leave it at that. Let's see here. That was number 5. Let's take a look at number 6. Okay, so then number 6 is evaluating a line integral. Okay, so we have this oriented curve C. And then we have the vector field F. Okay. So in order to evaluate the line integral, so we talked about how to do it before, so this one's not bad. I'll just set it up real quick. So first thing is we should parameterize our curve. So when your curve is a function of just a function of x, or just a function of a single variable, there's a natural way of parameterizing it, which is to just set your variable equal to your parameter. So if I just say like if x is t, then y would just be in terms of the parameter t squared. Okay. And so since the parameter t is just x, we'd have t ranging from -1 to 1. And incidentally, that gives us the correct orientation as well. So at -1, we are starting at this point. And then at 1, we'd be ending at this point. If you did want the opposite orientation, you can still use this parameterization. You would just negate, put a negative in front of your integral to get the right answer. Okay. So let's see, that's the parameterization of our curve. We need the derivative of that. Okay, and then to evaluate the integral, the line integral using our parameterization. So we'll set it up as an integral with t ranging from -1 to 1. And then remember, we take our vector field and evaluate it along the parameterization. And then we need a dot product with the tangent vector that we get from the derivative of our parameterization. Okay. So to evaluate the vector field along the parameterization, you just plug these in for x and y into your vector field. So x is t, y is t squared. So y squared will become t to the fourth, and x squared will become t squared. Let's dot with 1, 2t. So dot product will give me t to the fourth plus 2t cubed. And then you just need to finish evaluating this integral, okay? All right. So let's move on to number 7. Oof. Okay. Okay, so let's take a look at this problem. So we have a really, really long, nasty looking vector field here. But what we're trying to do is we're trying to evaluate a line integral of this vector field along some curve. So you could, I doubt trying to evaluate the line integral directly would be a good way to go. So for this problem, I have a suspicion that probably it's set up so that this vector field is a conservative vector field, in which case we could evaluate the line integral hopefully more easily if we are able to find a potential function for it. So let me talk a little bit about conservative vector fields first, and then we'll hope that this is a conservative vector field, and then We'll talk about how to find the potential function if it is, and then we will evaluate I'll at least talk about how to evaluate the line integral. Maybe I won't go through all of the work. I don't know. We'll see. So a vector field F is said to be a conservative vector field if it is equal to the gradient of some scalar field f, little f, okay? Now this scalar function, little f, it's sometimes people call it a potential function. So if you hear that terminology, it's probably just referring to little f. Some people prefer to do equals negative gradient of the potential function, but for we won't concern ourselves with that. Okay. Okay, so why are conservative vector fields important? So it has to do with what happens when you try to evaluate a line integral of a conservative vector field. So let's see what that would look like. So we would parameterize the curve, and then we'd apply this formula for evaluating the line integral. Now, if the vector field f is conservative, then we can replace it with since it's the gradient of little f, we can say this is the gradient of little f evaluated along the parameterization, and then dot product with the derivative of the parameterization. Okay, but when we look at what you have inside the integral, this is kind of like a derivative from a chain rule. So you kind of got like your derivative of your outside function evaluated at your inside function, and then times the derivative of your inside function. So the inside is really the result of doing the chain rule when you're trying to compute the derivative of little f composed with the parameterization. And what's nice about that is since you're integrating a derivative, the integral and the derivative just cancel out. So it will just leave you with f composed with s. And then you would just need to evaluate your bounds from a to b. So you'd have like s evaluated at s of b minus f evaluated at s of a. Now, s of a should be giving you the initial point of your curve. So let's call that point A. And then your parameterization evaluated at the final time b should give you the endpoint of the curve, which we'll call b. So this is really just going to be little f evaluated at the final point of the curve, and then minus little f evaluated at the initial point of the curve, okay? So this says that if your vector field is conservative, you can evaluate the line integral by simply taking its potential function, evaluating it at the endpoints of the curve, and then subtracting. So you wouldn't actually need to bother with parameterizing your curve and doing all this stuff, okay? Now, because the line integral depends only, so what we see is that the line integral depends only on the endpoints of the curve, and it doesn't actually matter what your curve is doing in between those points. So often people will say that a line integral of a conservative vector field is path independent then, because the path that you take doesn't matter. So here's like a different path from A to B. But if you integrate along this curve, you'd get the same result as integrating along the original one that I drew. So it doesn't depend on the path, but just the endpoints. So that's why they say that the line integral of a conservative vector field is path independent. And then kind of a special case that just maybe worth noting is if you had a closed curve, so one that ends where it begins, then you see that f of b minus f of a would just be equal to 0 in that case. So when you have a conservative vector field, the line integral along any closed curve will always be equal to 0, okay? So that's maybe a special case also worth noting. So let's look at the vector field that we were given, and let's try to see if we can find a potential function for it. So here was its x component. And so the y component is this. And then the z component is just ginormous. Okay, but here it is. So I want to check if it is equal to the gradient of some scalar function little f. Okay? Now, if it were equal to the gradient of some scalar function little f, so that means the partial of little f with respect to x should be equal to this. Now, partial of little f with respect to y should be the second component of the vector field, and partial with respect to z should be its third component. So let me write that out a bit more explicitly down here. Okay. So here's what we are going to do. So let's take one of these equations. So in theory, it doesn't matter which one, but you probably want to take one that's easier to work with. So I'm gonna take, I'll take fx first. It's not that difficult. So if this is the partial of f with respect to x, if I integrate the partial of f with respect to x, then I should recover the original function f. So let me start with this first, okay? So integrate fx with respect to x to get f. So that's going to give me x squared y e to the cosine squared of z, and then plus 2x. Okay, now, when we do this integral, we pick up a sort of arbitrary constant, if you will. But since we were integrating with respect to x, we were treating y and z as if they were constant. So this constant that we add at the end, it's actually not necessarily constant, but it could have some y's and z's in it as well, since they were treated as constant when we did the integral with respect to x, okay? So this is our function little f, but we haven't figured it out entirely. We haven't solved for it yet in the sense that we have this function of y and z, which is still unknown. So to try to figure out what this guy could be, we need to make use of these other equations. So what I'm going to do is I'm going to take what we currently have for f over here, and I'm going to first compute its derivative with respect to y, okay? So the partial of everything here with respect to y will be x squared, cosine squared z. That goes away, and then I'd have the partial derivative of this function with respect to y, okay? So now I'm going to compare the two expressions that I have for the partial of f with respect to y. Oh, and okay. I dropped the e, so I'll just add that back in. So comparing these two expressions, we see that the partial of c with respect to y must be equal to 2yz for these to be the same. Okay. So using that information, we can take this and integrate both sides with respect to y. So integrating with respect to y is going to give us the original function. So that's going to be y squared z. But again, we sort of pick up like plus some constant. And since we integrate it with respect to y, we treated z as if it were a constant. So what we end up with here is going to be possibly some expression involving z, so possibly some function of z as the arbitrary constant. Okay. So let me combine these two results now. So I'm just going to plug in what we found for c of yz. I'm going to plug it into what we found over here for f. So what we have right now is little f is x squared y e to the cosine squared z plus 2x and then plus y squared z and then plus this function c of z that we don't know just yet, okay? So we're still not done because we still don't know what this C of z should be. So to figure out what C of z is, I have this last equation down here, which I haven't made use of just yet. So what I'm going to do is take what I have for f here and compute its partial derivative with respect to z. So that's going to give me x squared y. Chain rule, so derivative of cosine squared will be 2 cosine z. And then there's a chain rule, so multiply by derivative of cosine. So we pick up a negative sign. And then we'll copy down the exponential. So that was the partial of this with respect to z. And then we have plus y squared from that. And then we're going to get plus c prime of z. Okay. So that's what we got from taking the partial of f up here with respect to z. Okay. And then comparing that with the expression that we have over here. So we have these two expressions for the partial of f with respect to z. So let me see here. This term matches this term. That's good. I have the y squared matching with the y squared here. So it looks like negative sine of z should be equal to c prime of z then, okay? So therefore, integrating this with respect to z will give us cosine of z for c of z. Okay. So now I'm going to take what I have for f and plug this in. So then we have little f equals x squared y e to the cosine squared of z plus 2x plus y squared z plus cosine z. Okay. Now, this integral technically gave us plus an arbitrary constant, this time being an actual constant. But then for us, we usually don't need to care about what this constant is. So for convenience, we usually just treat it as being equal to 0. So we get this for a potential function, all right? So it should be that the gradient of this function, it should be equal to the original vector field in our problem, okay? Now, just a sort of comment about this procedure. So if the vector field f were not conservative, then what would happen is, let's say when I get to maybe this step here where I'm comparing, so here this was like fy was equal to the second component of our vector field from the problem. And then this is coming from taking the partial derivative of f from this expression up here for f. So what happened was like this term matched with this term, and then we saw that this term had to match with this term. If our vector field were not conservative, then what might happen is maybe this term wouldn't match with this term. Or perhaps what you would get is that the partial of c with respect to y, it might have had to match with a term that had an x in it. So like if you get like c of yz, and then comparing to this, like it has to like. Okay, so here, let me try to write it out a little because I can't talk. So from here. So like since those are both equal to f partial of f with respect to y, they must have been equal to each other. So here it works really nicely that I can cancel these terms out. And then it leaves me with this partial derivative equaling this, okay? If your vector field were not conservative, what would have happened is after canceling anything out that you could have, you would have had something like this perhaps, as an example. So something like this would have happened where now on the right-hand side, we have something that should have been a function of y and z only. But on the left-hand side, we still have some x's left over after canceling what we could, okay? So then something like this is not possible, right? You can't have a function of y and z depending on x. So something like this would be an indication that your vector field were not conservative. And then you would either need to check your work more thoroughly to make sure you didn't make a mistake, or perhaps your vector field actually wasn't conservative in that problem, okay? Now, if you want to check if your vector field is conservative first before you try to find the function little f. You can use this fact that if f is conservative, then the curl of f should equal 0. So what you could have done is computed the curl of the vector field first to see if it was equal to 0. And then if it was equal to 0, that would suggest that it was conservative. And then you could go about what I did to get the scalar function little f. Whereas if the curl of f were not 0, you would know it was not conservative, and you would know not to try what I did, okay? Now, because the vector field was so complicated, I really did not want to try to compute its curl. So that's why I went straight away with just trying to solve for little f by doing all of this, okay? I suspect if you have a problem like this, integrating, like computing a line integral of such a complicated vector field, I suspect it's probably set up to be conservative, okay? Because otherwise the integral would be horrendous to try to compute. Okay, but since we have this result, let me copy it for the moment. All right, so I'll just paste it over here real quickly. Okay. Okay, so to evaluate the line integral of our vector field, so just skipping to the end result, what we can do is just take our function little f and evaluate it at the final point, and then minus the initial point of our curve. Now in the problem, our curve C, so let me write down that information. So in the problem, they gave us a parameterization for it already. And it was from 0 to 2 pi. Okay, so to get the initial point of the curve, you would plug in the initial value of t, which is 0. So that will give you 1, 0, 0. So that was the initial point. So here you'll have minus f evaluated at 1, 0, 0. And then plug in the final value of t into the parameterization to get the final point of the curve, 1, 0, 2 pi. Okay. So then now that we have that, just plug these into the function to get the answer. So y is 0, so that's 0. X is 1, so that's 2. 0. When z is 2 pi, that's plus 1. So plug in 0 for x, y, and z. So we still have 2 from x being 1. We're still going to have plus 1 from cosine of 0 being 1. So it looks like the final answer is 0, okay? Okay. Okay, so now that we did number 7, let's look at number 8 next. Oof. So we have a torus. Okay, so I'm going to, so it's talking about finding the tangent plane to a surface. So if your surface is described by an equation of the form, let me, okay. So if the surface is described by an equation of the form f of x by z equal to a constant, then you can get the tangent plane at a point x naught, y naught, z naught. So maybe specifically, you can get the equation of the tangent plane at this point x naught, y naught, z naught. So you can get the equation by taking the gradient vector evaluated at that point. And then gradient dot product with the vector x minus x naught, y minus y naught, z minus z naught. And then setting that equal to 0. Okay. Now, if I write this out explicitly, so remember the gradient is the vector of the partial derivatives of f. So if you do the dot product, you have like partial of f with respect to x times x minus x naught. So partial f with respect to x evaluated at your point, and then times x minus x naught, and then same thing with respect to y, times y minus y naught, and then plus partial with respect to z, times z minus z naught equals 0. So you could write it out more explicitly like this. Okay. So in our problem, we have the torus. And so they gave us the equation of the torus, which was, okay. So they wrote it as x squared plus y squared plus z squared plus 3 squared. They had this equal to 16 times x squared plus y squared. Now I've moved that 16 times x squared plus y squared term to the other side so that I'll have it equal to 0 like this. Okay. So the reason I move it over is so that I would have the equation in the form of like function x, y, z equal to a constant. Okay, so then now that I've done that, this function that I have here on the left-hand side, I need to compute its gradient in order to get the tangent plane. So I need the partials with respect to x, y, and z. So let's do the partial with respect to x first. So here I'm using the chain rule for that. So then we'd multiply by 2x. So I'll change it to 4x on the outside. And then here with respect to x will give me minus 32x. Let's see, with respect to y will be very similar. And then with respect to z, okay. All right, and then I would, so we need to evaluate at the point that they gave us, so 3 over 2 root 2, 3 over 2 root 2, and root 3 over 2. Now let me see if that's x, y, z. Okay, so 4x would be 6 over root 2. Now let's see, x squared plus y squared plus z squared. So x squared is 9 over 8. And then z squared is 3 over 4. So x squared plus y squared plus z squared should be 24 over 8, which is 3. So we'll have 3 plus 3 on the inside, so times 6. Let's see here, 32 times x, so 16, 18. So I think 18 over root 2. And we got the same thing for the y component. And then for z, root 3 over 2, so I guess 2 root 3 times 6. Okay. So 36 minus 18, so it's 18 over root 2, 18 over root 2, and 12 root 3. Okay. All right. Okay, so then to get the equation of the tangent plane, okay. Then I'm just going to use the terminology in the problem. So tangent plane, we start calling A to the torus T at the point P. The tangent plane to the torus T at the point P, which they're calling A. Okay, so I take the partial derivatives that we got from the gradient. Those become the coefficients over here. So taking the first one, 18 over root 2. So that was a partial with respect to x. And then, so times x minus x naught. X naught being 3 over 2 root 2. Next partial f with respect to y, which would be this, times y minus y naught, which was the same thing. And then here's the partial with respect to z that we found. That would be times z minus z naught. And then equals 0. Okay. So that would be the first part of the problem. That would be part A. But then there was also part B. So let's see what part B is. So it happens to also be tangent to the torus at this other point, minus P. Find and parameterize the line that lies on A and is perpendicular to the line from P to minus P. Okay. So here's sort of the picture that I'm seeing. I'm not going to draw the torus. For those of you who don't know, a torus is just a donut. But let's say here was the tangent plane, which was tangent to the torus at the point P, and also tangent to the torus at the point minus P. Okay. So then we have this line from minus p to p. And we're looking for So we were looking for a line that lies on the plane A, the tangent plane A, and it's also perpendicular to the line from P to minus P. Now, I suppose the question is not entirely well posed because there's more than one line that lies in the plane and is perpendicular to this line. So what I will do specifically is I will find the line that's in the plane, is perpendicular to this line, and specifically I'll find the one that is passing through the point P as well. Okay? So this line L here is the line that we would be looking for. Okay? Perpendicular to the line from minus P to P and lies inside of the tangent plane A. Okay? So here's how we will do that. So to get a parameterization of any line, there is this generic formula for parameterizing a line. So P represents a point that lies on the line. And then V is a direction vector for the line. So a vector that points along the line. Specifically, if you were to take the vector and attach it to the point P, then it would lie on the line L, okay? Okay, so I have chosen to find the line that will pass through the original point P in our problem. So we already have a point on the line. What I'm going to need is a direction vector. So to get the direction vector V, I know that V has to be perpendicular to this line segment. So then if I take the vector connecting from minus P to P, then the direction vector for the line that I am looking for, so it needs to be perpendicular to the vector connecting from minus P to P. So I'll write like this for now. And it also has to be, since it's inside the tangent plane, it has to be perpendicular to the normal vector of the tangent plane. So the gradient vector itself, the gradient vector that we found here, happens to be a normal vector for the tangent plane. So that's why when you do the dot product with this vector, you get 0, because this is representing a vector inside the tangent plane. So since this guy is normal to it, the dot product should be 0 because they're orthogonal. So that gradient vector then, being normal to the plane, should be in particular perpendicular to the line L, and therefore perpendicular to the direction vector V. So if it's perpendicular to both of these vectors, then I can find the direction of this vector I can find a direction for this vector by computing the cross product of the two of these vectors here, okay? So let's do that real quickly. So first, the vector connecting from one point to another point, you can compute it by taking the final point minus the initial points. Okay. So 2p would be 3 over root 2, 3 over root 2, and root 3. Okay. So just take p and multiply it by 2, and that's how I got that. And then the gradient, which we found earlier, was this guy over here. I'm just going to copy it down real quickly for reference. Okay. So the direction vector for the line that we are looking for is perpendicular to both of them. So therefore, to get something perpendicular to both of these guys, we'll do their cross product. So let me try to do that real quickly. So 36 root 3 over root 2, and then minus 18 root 3 over root 2. This should leave me with 18 root 3 over root 2. The next one will be same thing but negative. The last one is, what is that? 54 over 2, so 27 minus a negative, so plus, so 54, I think. So we could use this as a direction vector for the line. So then altogether, to get the parameterization of the line L, I'm going to take the point P that we initially had, which was, I guess I'll write it like this now. So it was 3 over 2 root 2, 3 over 2 root 2, and root 3 over 2. And then we'll add to that t times the direction vector, which we just computed down here. And then this would have given us one parameterization for the line L. Okay. All right, so now that we've taken care of that, let's move on to problem number 9, which I guess I'll just do over here. So let's look at number 9, which, let's see here, is going to be concerning the inverse function theorem. 1, 1. Okay. Okay, so this problem concerns the inverse function theorem, so let's talk about what that says. So if you have a vector field, so a function from Rn to Rn for some n, the inverse, and let's say this function f is a ck, meaning it's kth order partial derivatives exist in our continuous. So let's say it is a ck and some neighborhood of some point which I'll call P. So the inverse function theorem says if the derivative of f evaluated at the point P is invertible, which you can check by computing the matrix of partial derivatives and checking that the determinant is non-zero. So remember, determinant being non-zero is equivalent to being invertible. Okay. So it says if the derivative at P is invertible, then the function f will also be invertible in some neighborhood of this point P. And not only that, inverse function theorem also says that the inverse of f will be ck as well if the original f was ck. And then finally, to get the derivative of the inverse, we can kind of do that by using the chain rule. So we know that the inverse composed with the original f, well, f inverse and f should just cancel, leaving you with just x. So if you take the derivative of both sides of this equation, you get the derivative of f inverse evaluated at f of x, and then times the derivative of the inside, so times the derivative of f at x. Derivative of this guy is not 1, but the identity matrix, which I guess would be equal to 1 if there were a scalar. So then this tells you that the derivative of the inverse function evaluated at f of some point x would equal the inverse of the derivative of f evaluated at x. Okay. So we'll use that to answer this question here. So first, to show that it is invertible on some neighborhood of 1, 1, I'm going to go ahead and compute the derivative of f, specifically computing its matrix. So partial derivatives with respect to x are 2x and 3y. And then partials with respect to y are 2y and 3x. I'm going to evaluate at the point of interest, 1, 1. Check the determinant. Let's see here. Did I make a mistake? It's a partial with respect to x. So y is 2y and 3x. The point 1, 1. Determinant, however, is 0. Okay. So my suspicion is that there is a mistake in the problem. So I'm just kind of double checking everything right now. This is the function copied down correctly. It is the point 1, 1. Partial with respect to x, 2x, 3y. Partial with respect to y are 2y and 3x. But you plug in 1 and 1, and it's definitely not invertible. So the problem is not working out, but that's okay. I can make the problem work if I change the point 1, 1 to something else. So let's do that real quick. So let's just do like the point maybe 1, 2 would work better. Oops. Okay, so yeah, that totally didn't work with the point 1, 1, but let's try the point 1, 2 instead, all right? So I'm altering the problem just to show you guys how it would have worked if, it actually worked. Okay. So if we plug in the point 1, 2 for x and y, so this time we'll get 2, 3, but this would be 4 and 6. And now when we check the determinant, it's definitely not equal to 0 anymore. So then because the determinant is not 0, you can conclude by the inverse function theorem, which I'll just abbreviate as IFT. So by the inverse function theorem, you can see that the function f is invertible in some neighborhood of the point 1, 2. Yeah. And then if we want the derivative of f inverse, evaluated at the point f of 1, 2, so according to what I have here, the derivative of f inverse evaluated at f of 1, 2 should be the inverse of the derivative of f evaluated at 1, 2. Maybe writing it like this actually looks better. Okay. Okay. So the derivative of f at 1, 2 was this 2 by 2 matrix. So we need the inverse of it. So to get the inverse, it's 1 over the determinant. Then what you do is you swap what just happened? Okay, wow. Okay. So to get the inverse of a 2 by 2 matrix, you do 1 over the determinant. Then you swap the diagonal entries, so I'll write it as 3 and 2. And then you change the sign of the off-diagonal entries. Okay? And that's how you get the inverse of a 2 by 2. So then this would have been the derivative of, or at least the matrix of the derivative of the inverse, evaluated at the point f of 1, 2. Maybe not super important, but what is f of 1, 2? If x is 1 and y is 2, it looks like you'd get 5, 6. Okay. Yeah. So I think it's conceivable in a problem that you might be asked for the derivative at the point 5, 6. And you'd have to recognize that 5, 6 was f of 1, 2. And then from there, you would do what we did. Okay, so that was number 9. So then we'll look at number 10 next. Okay, so number 10 looks like a somewhat simple double integral. Let's try to work it out. Okay, so let's sketch the region of integration right now. Notice that you don't really want to do the integral with respect to x right now. So that means you probably want to switch the order of integration instead. But to do that, we need to figure out what the new bounds are going to be. And so to do that, we need a sketch of our region. So let's see, y is bounded from 0 to 1. And then x from 0 to cosine inverse of y. Now, when x is equal to cosine inverse of y, notice that is the same as saying that y is cosine of x. Okay? So y equals cosine of x, I know looks like this. And it hits 0 at an angle of pi over 2. Okay? So if x is bounded below by 0 and bounded above by this curve, then that refers to this region in here. So now to study the bounds with dy on the inside and dx on the outside. So starting with x on the outside, x ranges from 0 to pi over 2. And then for y, so the way that I think about setting up the bounds are on an integral is I start with the outside, so x ranges from 0 to pi over 2. And then on the inside, with respect to y, we would be treating x as if it were a constant. So imagine if you had some x value between 0 and pi over 2, and you're holding it constant. So for given constant value of x between 0 and pi over 2, what would the bounds on y be? So y would start at 0, so that would be like the lower bound of y. But it wouldn't go all the way up to 1, but rather the height that it goes up to is dependent on x. So different x values will give you a different upper bound on y. So the upper bound on y is always equal to cosine of x, because that was the equation of this curve. So then that gives you the upper bound like that. And oh, what did I do here? Why did I write down y? The lower bound of y is 0. Okay. So then that's a pretty straightforward integral. So you'll pick up a cosine of x. So it'll be like that. And then you can do this integral with a u substitution. I'll just leave it at that, okay? Okay, so let's look at the last one. So change of variables. Okay. So we're asked to evaluate this double integral. So R is the region bounded by xy equals 1, xy equals 3, y equals 2, and y equals 6. And it says to use this change of variables. The x is v over 6u, and y is 2u. Okay. It's maybe not super important, but I'll go ahead and sketch this region R first. You can sort of do the problem without the sketch though, but so I'll start by labeling y as 2 and y as 6 because those are the easier ones to do. Okay. Now xy equals 1, so that's like y is 1 over x. And I know y equals 1 over x is kind of like a hyperbola, kind of, with, in the first quadrant, it looks something like this. Or xy equals 1, I'll write it as. Now xy equals 3, or y is 3 over x, it would look similar to what I have here. It would be a little bit further out though, so I don't know, something like that. Okay. That's just a very rough sketch. So here's y equals 6, here's y equals 2. So then this funky region here would be the region R that we were trying to integrate over. Okay. So to apply the change of variables theorem, so let me do a couple of things right now. So first, we're converting the integral to be an integral in terms of u and v. So one thing we need to do is substitute these in for x and y. So here's x times y cubed. Okay. Now remember that when we do a change of variables, we need to multiply by the absolute value of the Jacobian of our transformation. So from our change of variables equations here, I need to compute the partial of x with respect to u, partial of y with respect to u, and then partial of x with respect to v, and partial of y with respect to v. Okay, so partial of x with respect to u is minus v over 6u squared. Partial of y with respect to u is, that's 0, and then this is 1 over 6u. So I do those partial derivatives, and now we need the determinant. Okay. And then in the for the change of variables, we multiply by the absolute value of the Jacobian here. So since I multiply by the absolute value, I'm going to drop the negative sign and just do 1 over 12u for the moment, okay? So that's not bad. But of course, we also need to figure out what the new region of integration is going to be. So I need to know what region in the UV plane is going to correspond to this region R in the XY plane. So to do that, usually what I do is I try to see how the boundaries get transformed. So let me start with this part of the boundary, which was xy equals 1. Here, if I take these equations and if I multiply them together, notice we get xy equals, so the u's cancel, it's 2v over 6, so v over 3. Okay. So that means when xy is equal to 1, that's equivalent to saying that v is equal to 3. And I guess likewise, when xy is equal to 3, you would get that v is equal to 9. Okay. So then these two edges of R correspond to v equals 3 and v equals 9 in the UV plane. So I have that right now. Let me see that. So the other ones were y equals 2 and y equals 6. And incidentally, we have y equals 2u. So if y is, oh geez, okay. So when y is equal to 2, that's equivalent to saying that u would be equal to 1. And when y is equal to 6, that would be equivalent to saying that u is equal to 3. Okay. So then let's see here, 1 and 3. Okay. All right, so then looks like our change of variables takes this rectangle on the UV plane and converts it into this region R in the XY plane. So I guess it's not that important at this point, but maybe I'll just kind of make a note of it. So specifically, this edge xy equals 1 corresponds to this edge v equals 3. Let's see here. This in blue over here. Oh, okay, whatever. All right, so when y was equal to 2, u was equal to 1, so that corresponds to this edge over here. Let's see here, xy equals 3. So this edge corresponds to, when xy is 3, that was the v equals 9 edge. And then finally, when y was equal to 6, that corresponded to when u is equal to 3. Okay. Okay. Okay, so let's see here. But the bounds on our new integral are u will be from 1 to 3. V will be from, what was V again? 3 to 9. Okay. So then, I'll leave it to you guys to finish evaluating the integral. I think it's been about 4-ish hours almost for me, so I'm ready to wrap things up with that. Now, so remember that when you're doing change of variables, when you get the Jacobian, just remember to do the multiplied by the absolute value of your Jacobian. So don't forget to do that if you need to. As a small side note, notice that, no, again, this isn't super important, but no, okay. Notice that in the XY region, if I go red, blue, green, and I guess whatever that color is, what is it? It's a counterclockwise orientation. But over here in the UV plane, if I try to go red, blue, green, and whatever this color is, it's opposite. It's clockwise, whereas this was counterclockwise. So that change in orientation is the reason why the determinant is negative. Negative determinant indicates change in orientation. Okay. But when you're doing a double integral like this, there shouldn't be any sense of like orientation, if you will. So that's why you always do absolute value. Okay. But okay, so I guess that's it. So I'll end my video at that.